In this paper, we propose a method that supports both free viewpoint relighting and scene composition, and can even relight real translucent objects. Here are some teaser results of our approach. Neural radiance fields, or NeRF, are highly effective for synthesizing novel views of a scene. However, NeRFs assume static scenes and fixed illumination. They infer the radiance along array after all light transport has occurred in a scene, so they cannot relight the captured objects or compose them into new scene configurations. Recent inverse rendering methods propose to jointly estimate lighting, material properties, and geometry from images. They can be used to relight the reconstructed objects, but they only model simple BRDFs that cannot deal with translucent objects. We propose a new neural object representation named Object-centric neural scattering functions, or OSFs. OSFs approximate the cumulative radiance transfer from an unobstructed distant light, which is expected to implicitly account for all subsurface radiance transport to X due to the distant light from direction omega light. Our OSF formulation is related to classical graphics concepts for modeling subsurface scattering effects, phase functions, and BSS RDFs, but with important differences. The process of light transport from an unobstructed distant light to a point X inside a translucent object is complex. 1. The distant light first hits the visible surface area. 2. The surface then transmits the light into the object interior. 3. The transmitted light scatters within the object. 4. Some light finally arrives at X from incoming directions omega in. 5. The arrived light scatters to directions omega out. Phase functions only model 4 and 5, so one has to account for the other steps by multiple integrations, which is computationally expensive. BSS RDFs encapsulate steps 2 through 5 and only model surface points, but one still has to integrate over the visible surface area. In contrast, our OSF formulation encapsulates the entire process that takes all 5 steps into account. This abstraction of modeling the whole process as cumulative radiance transfer eliminates the need of any integration, making it computationally tractable to use in neural volume rendering. Now let's look at the object-centric neural scattering function in detail. XYZ is the spatial location, phi I, theta I is the distant light direction, and phi O, theta O denotes the outgoing light direction. The object-centric neural scattering function can be modeled by a multi-layer perceptron neural network. It outputs ρr, ρg, and ρb, which denote the cumulative radiance transfer, which is defined as the ratio of the outgoing radiance for each color channel at this spatial location that is caused by an unobstructed distant light from direction phi I, theta I. And it also outputs the volume density at that location. In summary, OSF models a cumulative radiance transfer function rather than a radiance field modeled by NeRF. Now let's look at what is cumulative radiance transfer in detail. Consider a distant light with radiance L light from direction omega light. OSFs do not physically model subsurface scattering effects, but approximate this complex process by learning the cumulative radiance transfer at any spatial location X. It models the cumulative radiance transfer function ρ, which is defined as the ratio of the outgoing radiance in the direction of omega out at location X that is caused by an unobstructed distant light from direction omega light. The scattered outgoing radiance L out can then be easily obtained by multiplying the cumulative radiance transfer value with the radiance of the distant light. This approximation allows using a volumetric rendering formulation to learn from images, while being able to approximate the appearance of both translucent and opaque objects. As a result, OSFs can relight both translucent and opaque objects by learning from only 2D images. Next, we will show more qualitative results and comparisons against baseline methods.